Time for some more kitchen table astronomy with Hampshire College astronomer Dr. Salman Hameed, Mr. Universe, one of the folks behind Kainaat Studios. We'll do the shameless plug-a-thon at the beginning. One, it's the beginning of the NEPM Spring Fund Drive. So, we've been talking a lot about budget cuts and the importance of supporting things that you believe in a time like this. That's one option for you. You're a board member of Amherst Cinema. I'm going to be at Amherst Cinema tonight, hosting a Q&A with Michael Townsend for the Secret Mall apartment movie.
And you are president and the board member of the Shea Theater. And I was there just yesterday for Madeleine Peru in concert. And I have to say two things. First of all, the concert was amazing. Her voice is beautiful. And it was a show that was very political without being polemical. Mm-hmm. I thought the way she did that by simply reading quotations from Martin Luther King or
Shirley Chisholm, James Baldwin,
and Nelson Mandela.
Yeah,
and she didn't say things around it as much, and I thought that was brilliant.
Yeah, it really was.
She just read those things and she would just move on. And those quotations were about standing up, resisting, fighting, and sort of and the broad inequities that exist, just spelling those out. So I thought that was a really wonderful way. I think it's almost a great model that if you are going to do concerts or other types of things, how to resist, how to make political statements. This was a fantastic way of doing that. And
she'd read a quote from James Baldwin and then do a song that might be loosely connected to that quote, but otherwise just lets James Baldwin's quote sit there and then you contemplate it while you listen to the music.
Yeah, no, it was, and there was one song that was very powerful that she did. It is in her new album, and that is the most overtly political song. But other than that, again, absolutely wonderful concert.
And it was fun announcing her and then seeing you in the front row and then giving you a little shout out from the stage about listen tomorrow, he'll be on the show.
But I should mention, and I'm not saying this, Monty, because you are sitting here, but I would just say, this is the great thing about going to concerts in the Western Mass. First of all, you get really good acts, but also you can see them and hear them pretty close by. It's a Shea Theater. Every seat, I never worry about, those are actually great seats because it's a relatively small theater. But you can also get to the front row if you are on the mailing list and if you act quickly to the show that you want to go to. And so, I love being as close as I can, any concert. And so, it was just spectacular.
One more shameless plug. Astronomy on Tap returns tomorrow to New City Brewery in East Hampton.
Right. So, May 20th. Tuesday from 7 to 9, doors open 6:30, and there will be, so this has been going on since last year, once a month, third Tuesday, but this is the last one before the summer break. Mm-hmm. And in this one, you have Professor Mark Heyer from UMass, and he will be talking about how to turn astronomical data into music.
Speaking of concerts.
Exactly. And so those are actually cool softwares that you can do that. I don't know what he's going to exactly talk about, but you can actually, if you love music, if you love electronics, if you love astronomy, well, here is a combination of that. And
because as far as we understand, it's like reading a star map as a sheet of music, where if a star pops up right here, it plays a note. If a galaxy shows up, it maybe plays a longer or deeper or a more resounding note.
And you can program it of what note something would represent, and so you can actually do various things, and you can also which way you are scanning, or some random ways of scanning the image, and so there are multiple ways in which you can create that. And so Professor Mark Heyer is going to talk about that. And then a graduate student again at UMass Amherst, Victoria Salazar, she's going to be talking about how we all really are stardust.
Yes, very Joni Mitchell.
That's right, and not Kansas,
Yeah,
we are dust in the stars,
dust in the wind. Yeah.
No, in interstellar space.
And that is tomorrow. Astronomy on Tap, New City Brewery. What time again?
At 7. Doors open at 6:30.
Now we're going to talk about LRDs.
Yes, I know, Monty, you love acronyms, and especially astronomy acronyms, because those have deep philosophical meanings behind it.
It's really just the laziness of astronomers to come up with better names.
That's why we have the Very Large Array, VLA.
Yeah, it's rarely the name of a telescope. Very Large Array. That's it? That's all you could come up with?
LBT, Large Binocular Telescope. Unfortunately, I'm not making this up. So anyway, so you can keep on going through this list. So LRDs are little red dots.
Oh my word.
So, okay, now the name sounds a little, they don't seem very exciting, and it almost reminds you of that you shouldn't walk through a jungle by yourself and don't talk to a wolf or something like that. But no, little red dots are actually about galaxies that James Webb Space Telescope have detected. And these are some of the farthest galaxies in the universe, which also means that they are the earliest, meaning to say that these galaxies were, the light that we are getting from them now started its journey a few 100 million years after the Big Bang. So these are the farthest objects from us and the earliest in the universe. And James Webb Space Telescope, again, a new instrument. So this is one of the things that happened. You launch a telescope, which is brand new. It's looking at particular wavelengths. And obviously, this is a new grand telescope. You spend $1 billion or more, a few $1 billion on it, in order to explore regions of light and things that you can do which have not been done before. And if you do that, you are going to find things, and you certainly hope, that nobody has seen them before. And so there was this puzzle that the James Webb Space Telescope, at some of its deepest images, were seeing these little red dots that were galaxies. We knew those, or they looked like galaxies. And there was a puzzling of what are they? And so now, and this was the genesis of some of the claims that 2 years ago or a couple of years ago, including started from 2 years ago, and then last year it certainly made a lot of headlines, that James Webb Space Telescope may have broken the universe. Not a fan of that statement because it leads to a lot of misconceptions, but I know why some people may use it, because it is a sexy phrase in that sense. People go like, oh, suddenly, your attention level goes up. But the reason why people had made that statement was because it looked like that these galaxies, some of these, were too big to have been formed early in the universe. So
it challenges the notion of what we think we know about the early universe, that these first galaxies would be much smaller, but these things that James Webb has picked up, bigger than astronomers were expecting them to be.
Right. And so I just want to say a couple of things. One is, all we are seeing is light. Then we have to interpret what that light means. Mm-hmm. And so the assumptions are, okay, well, later on, something like this would be, for example, all of that light would be coming from stars. And if that is the case, you can actually measure how bright these galaxies are, and you can figure out how many stars would be producing this light. And if you use those, and even there you have to actually use different models to predict how many types of stars are there, how many stars are producing this light, then you can figure out how big the galaxy is. Mm-hmm. And using those standard models, it looked like these galaxies were too massive, meaning to say it looked like a few 100 million years after the Big Bang, these galaxies had already produced stars that were too many to have been able to form by that time. So it looked like impossible. But of course, within astronomy, if something like this happens, and it's about any extraordinary claims, especially about overthrowing foundational ideas, you go like, are there any other explanations? Mm-hmm. And people have been looking at it, and one of the possibilities was that, well, maybe the light that we are seeing in these galaxies, in the little red dots, LRDs actually sound more scientific.
Yeah, they do.
Whether that is coming from something else other than just stars. And so just a quick thing, the reason why these galaxies are red are for two reasons. One is because they are really, really far away, so the universe expands. So the light gets redshifted. So part of the reason is that they are so far away, some of the farthest galaxies, so their light has been redshifted, and that's the reason James Webb Space Telescope can also detect it, because it works in the infrared, in the far infrared.
And remember, colors are part of the wavelengths, so the wavelengths of infrared are longer.
That's right.
So it's shifted because it's farther away as opposed to ultraviolet,
which is smaller.
Smaller.
But apart from that, these galaxies are really red as well. And that could be because there is a lot of dust in there. So what dust does is that it absorbs more of the blue light and let go of the red or the infrared light. And so these type of galaxies shows that whatever there is, it's enshrouded in dust. Now the question was, okay, so what is that? And so one of the ideas was, which we know that pretty much in all major galaxies, you have a supermassive black hole in the middle. And so could there be a black hole, supermassive black hole that is powering this light and not just stars? And then the question comes in, well, but how much? So in the universe, and we call it sort of like, more relatively nearby universe, which means that in our neighborhood, or at least 1 billion years after the Big Bang, these supermassive black holes contribute only 0.1% of the total mass of the galaxy. Meaning to say that contribution is relatively little. People think about, oh my goodness, there's a supermassive black hole. Is everything going to be sucked in? No, because the mass of a black hole, for example, for our own Milky Way, is relatively small compared to the total number of stars in the galaxy. So if that was the case, you can extrapolate. You go like, well, we look in the universe later on, which we can actually really observe well, we look like that the contribution from these supermassive black holes is much smaller, and most of the contribution comes from the stars. And you can extrapolate that to the early universe, and you say, if that is the case, then these galaxies have most of the light coming from stars. Mm-hmm. But it's an extrapolation, and it's an assumption. So that's what people were trying to look at, and
that's what broke the universe.
It could have broken the universe,
right?
But so there were other studies that started to look at from James Webb Space Telescope and looked at, well, what's going on with these galaxies, and they started to find that this ratio of supermassive black hole with respect to the size of the galaxy, it's actually very well formed in the rest of the universe. Later on in the universe, it's actually a good correlation. It seemed to actually be much more variable in the early universe. Sometimes it was about 1%, the mass of the full galaxy, instead of 0.1. Sometimes it was 10%. And in one case, it was 50%, meaning to say the light that you are seeing, 50% was coming from supermassive black hole and 50% was coming from stars.
And coming from a supermassive black hole, it's the accretion disk around the supermassive black hole. Black hole is a black hole. There's no light coming out of it at all.
That's correct.
There is a disk around it that things heat up and spin into, and then it just shoots light out.
And you need a lot of, what that means is that you also have to throw in a lot of material into that accretion disk that it can actually spin around, and before going in, it actually goes up. So those are all things are part of that. So already there were signs that, well, that nice relationship, which sort of like, usually it's about 0.1%, it seems like that's not the case in the early universe. And then what do you do? Well, a census. And so Astronomers One actually group, a paper came out, they actually looked at close to around 340 LRDs, the little red dots. So it's not just 1, 2, 3, 4. They looked at, hey, here is a population of these galaxies that we have. Let's look at as a group. And then what they found was that 70 to 80% of them definitely had these supermassive black holes in the middle. One of the puzzling thing was that these supermassive black holes early in the universe were not showing one key signature, their emission in X-rays, which are a key signature later on in the universe, because these supermassive black holes have those X-rays in there. But it was rarely seen in 1 or 2 of these LRDs. So that was a puzzling thing. So that's the next level of puzzle. It looks like 70 to 80% of these LRDs at least have supermassive black holes. And now they're figuring out, but why are they not showing other signs of supermassive black holes? And people think that it's because of being surrounded in a cocoon, maybe, of dust that is covering them. So one question that you might ask, or people who are listening might ask, what happened to them? I mean, why we don't see these LRDs later on in the universe? We don't have the same analogs because they should be there. I mean, we are looking at it 13 billion or 12 billion years ago. Well, but what happened to those galaxies? What are those galaxies today? Well, we think, and so this is where these kind of links come in. We're trying to figure out, well, this will tell you about how galaxies evolve. So if those were the galaxies earlier on, the black holes were much bigger. What that suggests is that perhaps black holes play a much bigger role in the evolution of the galaxy, because the other possibility would have been, well, yeah, black holes happen to be there, but they are much smaller compared to the larger galaxy that, yeah, they evolve with the galaxy, but they don't have much impact. These LRDs suggest that quite likely these supermassive black holes are actually playing a much bigger role in the evolution of galaxies, and by the time you come in a few billion years later, they have cleared out that cocoon and you don't see the same kind of shroudedness, but instead you see X-rays and ultraviolet light that is the usual signatures of these supermassive black holes.
So they shed their big cloud of dust that's making them look red. Some of the things that were in there that we can see in older galaxies, or I guess younger galaxies,
yeah,
is X-rays and stuff start to show up again. Because I think people who don't think about this a lot may forget that when you're looking at these galaxies from 100 million years after the Big Bang, that light is only reaching us now. So it's like it mailed us a baby photo of this baby galaxy that's only 100 million years old, as opposed to 4.5 billion years old, like our galaxy. And we're now just receiving the baby photo of the 100 million year old galaxy. It is only now just reaching us. So we are literally looking back in time at what galaxies were doing 100 million years after the Big Bang.
And you cannot see that galaxy evolve.
Unless we wait a billion years and take a look at it again, and then we'll see an adolescent photo of the galaxy.
But what you can do is to look at other populations of galaxies, and that's what makes this all challenging, because you would try to say, okay, well, those type of galaxies, I mean, those are not unique special galaxies, but they must have evolved later on. But what kind of galaxies that we see later on might have been like this when they were younger? And and again, I want to emphasize another thing, and that is, this doesn't mean that it solves the problem. This is an area of active research. We talked about exoplanet life, potential life on a completely different scale. Last couple of weeks, we talked about a potential signature of potential biosignature and atmosphere of the exoplanet K218b. That's an area of active research. There is a lot of debate going on of what that means and how can you make other tests to figure out whether that biosignature is real or not, what that exoplanet is. This is the same way. If you think, oh, this problem has been solved, I mean, the way I told you the story to a certain degree is that, well, there was this idea that the universe had been broken or whatever, but then here is an explanation of how it might have not have been. But this is not the end of the story. We are actually in the middle of it. So there are a lot of active conversations, active papers, active research going on. Some of it is actually at UMass Amherst as well, about, is this really true about supermassive black holes? And also, wait a minute, but these black holes are pretty big. How did that came about in such an early time in the universe? Because you also have to grow these supermassive black holes. Now we think with these LRDs that those supermassive black holes are actually relatively smaller in size at the time. Again, compared to the galaxy, they're bigger, but they are smaller than some of the regular supermassive black holes we see later on in the universe. So we think that what we are seeing is the growth of these supermassive black holes alongside with the growth of stars in the galaxy as well. But how did those first supermassive black holes form? We don't know, because one way is to use stars to form these supermassive black holes, or they may have formed by direct collapse of some gas clouds. Is that true? We don't know. So this is just a very early phase of understanding some of these early galaxies. And sometimes it's just fun to talk about that when you are something in the middle of a research thing and there's a lot of uncertainty, And it's a lot of fun, but sometimes it's not great for the public because they go like, oh, wait a minute, but what is the answer? We don't know.
You have to be comfortable with not knowing. And it doesn't mean that the universe is broken, and it doesn't mean that science doesn't work. It means, please be patient with us. Science is currently working.
And 2 quick comments. This science, I have to plug this in, thanks to NASA. Because James Webb Space Telescope is a NASA telescope, and also the research that funds it is also comes from NASA, because there is a threat of 50% cuts to people who do science, who do interpretations of this data, also is funded by NASA and NSF, but in particular from NASA. And second thing, if I can just close the loop from Medellin, Peru. Well, that's a big loop coming in. I was just thinking about it because I knew we were going to talk about this, and I was thinking about these galaxies to try to imagine. These are crazy scales that we are talking about. We are talking from a planet in a galaxy. We are sort of far away from the center of our own galaxy, and we are talking about these galaxies which are earliest in the whole universe. And then I was listening to Medellin, Peru, and she has this beautiful voice, and to me it was one of those things that, yes, it's really important. Sometimes scientists are at fault of thinking science is the only thing. This is one of the most amazing thing that humans can do, science. Actually, that is not true. Listening to Medellin, Peru, and listening to this music, I was like, this is amazing. That humans can actually produce this music on this tiny little planet in a galaxy. And there is, I was just thinking about it, but there is so much truth. And again, in that context, in the music, in the arts, of course, that extends all the way to paintings or films, of course, and other kinds of things. But I was just struck by it last night because thinking about these galaxies alongside listening to Medellin, Peru, I was like, this music. Just think about it. What a beautiful truth that we have, for example, that humans can produce. And so, just a big plug for that. It was on my mind. I thought I'll add it.
See, it takes us back to the beginning, the shameless plugging. NASA needs your support to study the science. The arts need your support, which have been defunded.
That's right.
So that we can connect with the better angels of our human spirit, the music of the spheres, even if you will. And also, public radio needs your support because we're right in the middle of a fund drive right now again.
And all of those things, it just makes you better human. Learning about galaxies, learning about music, learning about arts, and supporting public media.